We have seen that every move of the deterministic Turing machine has only one output, means your deterministic Turing machine from one configuration it will go to the only the next configuration, means it is not having the choices for the configuration. Now here we see the situation where your Turing machine maybe possibly have many choices to go from one configuration to other configurations. Here we see a non-deterministic Turing machine, NTM, a non-deterministic Turing machine, which we denote by writing the NTM, non-deterministic Turing machine, is a five tuple. T is equal to Q sigma tau Q0 and delta. Where, as we have seen in basic Turing machine, the NTM is also defined the same way as the basic Turing machine, means Q is the finite set of states, and what we assume that the halting states HA and HR does not belongs to the Q, means HA and HR are not the elements of Q. Sigma, again this is the finite set of alphabet symbol. Tau is finite set of tape symbol we have, and we again assume that sigma is the subset of tau as we have seen in the ordinary Turing machine, and also the blank symbol is not a member of the tau. Q0 is the initial state, and your Turing machine begins with this initial state. Q is the finite set of states, HA and HR are not in the Q. Sigma is the finite set of input symbols. Tau is finite set of tape symbols with sigma is the subset of tau. Blank is not an element of tau. Q0 is the initial state, that is an element of Q. And this is the same as we have defined in case of the ordinary Turing machine. Here, the important difference in the case of the NTM is transition function. So here we have the transition function delta. So transition function delta will be like this: Q sigma tau union blank. So you are in some state and you have some, your tape head is getting the symbol from the tau, or it may be the blank. From this you have the value of this transition function. Instead of having only one element, it is the subsets. So subsets of the set Q union HA HR tau union blank, and you can have the directions L, R and S. So the transition function is, in case of the Turing NTM, non-deterministic Turing machine, is not taking only one value. Instead, it is a subset of the set. So value of the transition functions are subsets of the set Q union HA HR, tau union blank, and LRS. So here, instead of only one output, you may have possibly more than one output. So, and in this case, one important thing is that the delta is now, in case of the NTM, delta is not a partial function, as in this case, it is allowed to take the value empty set. So here, in case of the NTM, delta is not a partial function, as once it is not defined, it means you can say the empty state. So it is allowed to take the null set, which is the subset of the set Q union HA HR, tau union blank, and LRS. So you can say your Turing machine in some state, maybe in the state P, and your tape head is carrying the symbol X, where X can be what? X can be any tape symbol or it can be blank. And P is an element of Q. Now, in this case, the value of this transition function can be more than 1. So like you can say that from this state, your machine may go to the state, say R, and it can modify the tape symbol from R to say Y, and it can move the tape head, say D. D can be what? You can say D1. So D1 can be anything, either L or S. So this is one output. Other output can be your machine can go to the S, and your tape symbol can be, you can write the tape symbol as Z, and it can move the tape head to the either left side or right side. So again, here D1, in this case you can say this may be D2, and here D2 is also can take the value from the set L or S. So these are the possible outputs. So here you have the output like this. Now in this case your machine has choice whether it can take this value or whether it can take this value, where S or an S can be or an S, okay, belongs to Q union HA HR. So R can be any states from the Q, or it can be any halting state, and S can also be any state from the Q, or it can also be the halting state. So your machine from the state P, it can go to even halting state. So R can be halting state, okay, or any elements from the Q. S can also be the halting state or any elements from the Q. So here, with the help of the transition diagram, you can say that you are in the state P, okay, you are in the state P, and you are going to the state R. So you have the state R, you are going to the state R for what? From the P, if you have the tape symbol is X, and you are modifying the tape symbol as Y, and you are moving the tape head D1. From the P, you can also go to the other state like S. You may go to the S, and once you are going to the S, then you can modify the symbol X to Z, and you may move the tape head according to the direction D2. And D2 can be left, right, or stationary. D1 can also be left, right, or stationary. X and Y can be same. So here X is any tape symbol or blank, and Y is also any tape symbol or blank, and Z is also any tape symbol or blank. So this is the situation, you can say. This means starting from this configuration, your machine goes to this configuration, or starting from this configuration, your machine can go to the this configuration. So here you have the two different possible configuration. From one configuration, your machine has choice to go for this configuration, or machine has choice to go for this configuration. And this is the case of the non-determinism. When you are in the same state and your tape head is scanning the symbol X, then your machine has this choice. And once your machine has this choice, then this is the case of non-determinism. So machine is going to make the choice whether I should go to the state R or whether I should go to the state S, and according to the transitions, you are modifying the tape symbol and you are moving the tape heads. So this is one situation, and you know that the deterministic Turing machine is the trivial case of the NTM, non-deterministic Turing machine, where always you have the unique output. And here your output can be any subsets. But however, you have some fixed choices. You are not, your machine is not allowed to take the infinite choices. We have some fixed choice, and your machine can opt, can think, can guess that which choice it has to execute. The configuration of machine is here in the same as in case of the deterministic Turing machine. Your machine, your NTM can go from one configuration to the other configuration. Means your NTM maybe from the configuration like P, this is the current state of your machine, and you may have the say X1, A1, and Y1. So this may be the one configuration. So your machine is in the configuration which is P is the current state, X1 is the X1 and Y1. These are the strings from the either tape symbol or you have the blank. So either tape symbol or blank. So and A1 can be either tape symbol or it can also be blank. And first symbol of the X1 is at the square 0, and Y1 again, Y1 has the restriction that the last symbol should be non-blank. The Y1 contains non-blank symbol at the last. So from this configuration, your machine can make the sequence of moves, and by making the sequence of moves, your Turing machine may be able to reach the configuration. Say, it can go to the configuration like Q. Q can be any state. Q can be any state, or Q can be HA or HR. So Q can be halting states also, or Q can be any non-halting state. So your machine can go to some Turing machine T is going to make the sequence of 0 or more moves, and it is able to reach the configuration Q. Say you have some configuration like X2, A2, and Y2, and your tape head may scanning the symbol A2. Here X2 and Y2, again X2, X2, and Y2, again they are from the tau union blank symbol. These are the strings from this set, can be taken from this set. And here A2 can be either tape symbol or it can be blank. And here the PQ can be any non-halting state or any halting states you have. So this is the configuration. So when Q is your halting states, then your machine halts for the input. Here, in case of the non-deterministic Turing machine, the output is not is is the things you can say that the because this is the non-deterministic Turing machine, then it can your non-deterministic Turing machine can possibly produce many outputs, and you have to see that which output leads to the successful terminations. So in case of Turing machine is going to make the guess, and for some guess it may produce some different output. For some other guess it may go for the some different output. And once your Turing machine finds the and comes to know that the input can be accepted if it is going for the accepting the language as a language acceptor, then when Turing machine concludes that okay, yes, the string is in the given language, it can halt. And once it halts, we will say that yes, string is in the given language. Or your NTM can compute the function, and once it is going to compute the function, then for some choices it can go for the successful termination of the function, and it has the output. So here, if you are having the Turing machine, and since this is the non-deterministic Turing machine, Turing machine may have the choices in certain points or at every state or at every from every configuration, your Turing machine may have choice. So your Turing machine may have choice in some configuration, or at every configuration, machine has the choices. But when you have the choices, it has some fixed number of choices. So see, if you are supplying some input and if you have designed the Turing machine for as a language acceptor, then your Turing machine can execute the choice, and in one choice, if it is not going to conclude that this is in the language, then it can go for possibly some other choices. So it has to execute the choices, and if at least one such choice is there for which your Turing machine goes to the halt state, your Turing machine goes halts in the state HA for the given input, then you can say that the input is accepted. So as soon as you are executing one choice, and if you are not able, your Turing machine is crashed, it means you are not able to conclude that the input is in the language, then possibly you have to explore some other choices if there is some other choice available. So you can make the decision, you can make your conclusion at the end of exercising all such choices. So if you are making all choices of moves, and in all choices of the move, if NTM is no longer is going to determine whether this is to say that the input is in the language, then it is going to crash. And if at least one such choice is there, then you can say that yes, the input is accepted. So there is a theorem: the language accepted by the T2 is the same as language accepted by the T1. So the theorem says that whenever you have the non-deterministic Turing machine T1, then there is an ordinary, or which ordinary means we are talking about the deterministic Turing machine T2, such that the language accepted by the deterministic Turing machine is the same as language accepted by the non-deterministic machine. So here this theorem actually says that Turing machine is, even in the basic form, is much more powerful, and it is so powerful you are not able to add more power in the basic Turing machine. Even you can go for the non-determinism. So the Turing machine itself is the much more powerful model of the computations. So here actually your Turing machine, if you are talking about the NTM, then NTM can have many choices. However, we can assume that there are some fixed choices, and let us assume for the simplicity, we have the two choices, means there are two possible moves at every state. So once you have the two possible moves from every state, this is for the simplicity, we can assume that. However, you can have two choices from some state, or you can have more than three choices from some other state, or you may have only one choice in some other state. So for simplicity, we assume that we have the Turing machine NTM, non-deterministic Turing machine, and in this non-deterministic Turing machine, from every state we are having the two moves. So we can say the move 0, we can give the number. So we have the two moves. Assumption, we have we assuming at every state NTM is having two moves. So let us name the moves like move 0 and move 1. So it is going to make the moves two moves. Then how you can, your Turing machine is going to start actually from the configuration. Say your Turing machine may start from the initial configuration. This may be the initial configuration, and from the initial configuration your machine has two choices. So your machine has two moves, possible moves. move number 0. Here you are talking about the move 0. It is not 0 or 1, it is just move number 0. So move number 0, it can go to this move number 0, and or it can go to the move number 1. Here this is the move. We are writing arbitrary. You can have here 1, you can have here 0. It is not the matter. So once your Turing machine is going to exercise the move 0, then it may go to this configuration. And this is actually, these are the configuration of the machine. So node is showing the configuration, and this is the root, and your machine is starting from the, you can say, this, it is going to start at the initial configuration. So once you are at this configuration by exercising the move number 0, then again your Turing machine has two moves. So it can exercise the move, okay. So it can go to the other possible configuration by exercising the move 0, or it can go to other configuration by exercising the move 1. If your Turing machine is having this move, then from here it can go to this configuration, okay, or it can go to this configuration by exercising the move number 1. Now here, from this configuration, your machine can go to some different configuration. This by exercising the move number 2. We have assumed that at every state we have the two moves, and we are having the move number 0 or move number 1. So your Turing machine is like this. Exercising the move, it goes to this place. From here, your Turing machine may go to this place, and your Turing machine may also go to this configuration by exercising this move. And your Turing machine may go to this place, or your Turing machine may go to this configuration while exercising the two different moves. So for one choice, move number 0, it goes to this configuration. For other choice, executing the move number 1, your Turing machine goes to this. And so this is the non-deterministic computation actually. So actually this is non-deterministic computation. Okay. So what is there? Actually, once these nodes, actually, these are the nodes, and these are corresponds to the configuration of your machine. So these are the configurations you have. These are the configuration. So your machine starts from the initial configuration, and we have assumed that if every state from every position, from every state machine has to make the guess, and here machine has the two possible guess at every state. So the computation tree for the non-deterministic case will look like this. So here the machine has two choices. Either it can make the 0 moves, or it can make the move number 1. Here also it can have the move number 0, or you can go for the other moves, which is move number 1, move number 0, or move number 1. So in this case, these are the choices, and if it is following, if your NTM is following this choice, say it is executing the move number 1, then again once it is at this place, it is going to assume, it is going to execute the move number 1 again. If you have the two choices, then it can go for the move number 1, then it is in some this configuration, it can reach to this configuration. Otherwise, if your Turing machine can make this moves 1, then again 1, then it can go for the move number 0, then Turing machine is at this configuration. If Turing machine goes for the 1, then 0, then 1, then it is in this configuration. And so actually the tree can grow infinite also, and the leaves of this tree corresponds to the halting conditions of the Turing machine. Turing machine can halt, or Turing machine may crash. Okay, so these are the leaves. So leaf nodes are corresponds to the halting situations. So now see that if we have the Turing machine like this, at every state your machine is supposed to make the guess, and we know that once we are going to make the guess, this is the case of non-determinism, and non-deterministic algorithm generally we cannot execute with our present programming languages. So, but this non-determinism we thought with the intuition that your machine is intelligent enough, and once your machine is intelligent enough, then it is able to make the correct decision at every state. Say your if your machine is at the state at this configuration, initial configuration, and it has once it has the two choices of moves, then your machine, we assume that your machine is able to make the correct moves. If answer is available, what we guarantee that if say if for executing the move number 0, if you are getting the answer, then your machine must make this move. So we assume that your machine is much more powerful, and at every state it is going to make the correct guess. So once machine is at this configuration, okay, it is going to make the correct guess whether it can go for this move number 0 or whether it can go for the move number 1. So and for that actually we are not going to provide any explicit algorithm to tell the machine that okay how you are going to make this choice, but we assume that machine is going to make the choice, and it is going to output. So machine is going to make the choice, and for the move number 0 or 1, and at every stage, say at the state xi, machine is going to make the choice, and I can be 1 to n. Okay, so n can be anything. So at every state, say at state 1, you are going to make the step 1, your machine is going to make the choice like this. Maybe your machine is going to start from this place, and if this is your thing that okay at this step what is the choice for the machine. So machine execute this choice actually, choice from 0, either 0 moves or it can go to the move number 1. But you are not telling explicitly, you are not writing the Turing machine for how you are going to make this choice. We are not writing any algorithm to tell the machine that okay you have to make the choice this. Otherwise, once you are telling the machine how you are going to make this choice, then this is the case of deterministic one. So we assume that machine is intelligent enough and machine is going to make the correct choice. So at every state, so at every step or from every state, once it has to make the guess, then from that state machine has to make the unique choice. Then once machine is at this place, again it has the choices, and we think again that okay machine is going to make the choice, and what is the beauty of this choice is what we assume that your machine is going to make the choice and it is independent of the choices, whether it can make the choice in the nth step or it can make the choice in some intermediate step, whatever time it takes, it is remains same. So this is the constant time. Actually this function has the constant time. So at every time you take, you need the same time to make the choice, and if such correct choice available for which you are getting the answer, then your machine must make the correct choice. So like this, if machine is at this place, machine from 0 or 1 it can make the choice, and say from this your machine is going to make this choice, and it comes to this place. So from this place it goes to this place, then it is coming to again it has the choice, and machine may follow this choice like this, and so on. So here you can say your tree can be of infinite, your tree can be infinite, your tree can be finite or your tree can be infinite, and in this way your Turing machine is going to making the choices, and you it is going to determine the correct choice by its own intelligence. And in this is the way that once if by making the moves, your Turing machine is going to make the moves, and it is finding out the correct choice every time by guessing by its own intelligence. And we can say that the how many steps your Turing machine needs to follow this non-deterministically. Non-deterministically means we assume that machine is intelligent enough and at every state it is going to make the correct choice. So and constant time is needed to decide whether to go this way or this way. So here also machine, Turing machine takes constant time to decide whether to go this way or this way. From here it can go to this. So question is that if such choice is available, if correct choice is available for which there is a successful termination, you will have the answer, then your non-deterministic Turing machine must make the correct choice. And if the number of steps it follows is polynomial, so number of steps of this machine is polynomial, the non-deterministic polynomial time means you have the polynomial number of steps machine is going to make for getting the correct answer. Then we will say that this is the your this your machine having the non-deterministically polynomial time it takes to decide whether you are getting the answer or you are not getting the answer. So this is the non-deterministically, this one I'm saying that this is non-deterministic. If you have the polynomial number of steps, you need to move non-deterministically to decide whether you have the answer or whether you don't have the answer. Then this is the resulting complexity of your Turing machine is actually non-deterministic polynomial time. So you have the non-deterministic polynomial time. So this is the way. So here actually you know that we don't have such programming language available that can make the choice, and at every state it takes the constant time. If you go for the implementation in your present programming languages, then you have to explicitly mention that how you are going to make this choice. So this is the way your non-deterministic Turing machine is going to compute. So at every state your Turing machine is going to make the guess and it is going to compute. However, once you go for the deterministic cases, like if you have the T2, like T2 is the deterministic Turing machine. To obtain the deterministic Turing machine from this NTM, actually, what you need actually, you need to exercise this choice, and you tell that okay, how you are going to make this choice. So how you can execute the choices, every choices by making some arbitrary order. You can fix some order and accordingly you can execute all possible choices. So your deterministic Turing machine's job is to search the answers in this tree. So once you, this is the tree, non-deterministic computation tree, and in this tree your deterministic machine is going to search the answer. Now, searching can be done in depth first manner or searching can be done in breadth first manner. So, see, this tree can be infinite, it can go to infinite. So, if you go for the, it may have the infinite, tree may be infinite. So, you may go to the, if you go for the depth first search, then your deterministic Turing machine may go to the, may loops forever, you can say that. So in order to guarantee that okay, your deterministic Turing machine should hold, if your NTM is going to hold, then actually you have to perform the some breadth first manner. The search can be according to the breadth first manner. So you need to make your deterministic Turing machine is supposed to make one moves sequence of one all possible one moves. Say it can go for this choice, then this choice. These are the two possible one moves. Then it can go for the all possible sequence of two moves. So your deterministic Turing machine can go for the all possible sequence of two moves. So if you perform the two moves, then you are here. Then this, if you perform the two moves, then you are here. Then if you go for the two moves, then you are here. Then it can perform the all possible three moves. So you are here, you are here. So it is going to find out the solutions level by level, and in this way you guarantee that when your NTM is going to halt for some input, then your deterministic Turing machine can also halt. So your job of the deterministic Turing machine is to search in the tree. So this is whenever you go for the deterministic cases, then you have to exercise the choices, okay, and you have to go for the one choices, and if for all possible choices if you are not getting the answer, then you will have the, you can say that yes, the Turing machine is, in this way you can say that Turing machine is going to crash, and it says that okay, yes, I'm not going to getting the answer. Or if you have designed the Turing machine as the language acceptor, then you will tell that yes, that input is not in the language, because for that your Turing machine is not going to halt in HA, your Turing machine will crash. So leaves of these node tree are corresponds to the halting state, maybe HR or maybe HA, okay, or so this is the way you can say that your non-deterministic Turing machine is going to work. So this theorem, with the help of this theorem, we come to know that you are not able to add the power of basic Turing machine. So the power of NTM and power of basic Turing machine is remains same. Whereas we have seen in case of the PDA, you know that for the language of palindrome, we don't have the deterministic PDA. So here, in case of the PDA, deterministic PDA and non-deterministic PDA have different powers. You have added the more power in the non-deterministic PDA. However, in the case of the NTM, ordinary Turing machine in its basic form is much more powerful, and hence you are failed to add more power. Even you can go for the non-deterministic cases. So even you can think about the non-deterministic Turing machine, you are not unable to add the power in the machine. So your Turing machine, which is the basic Turing machine, or you can say ordinary Turing machine we have discussed, that is the deterministic one, is much more powerful model of computations.